Right.
They counter in the class, just check them, they'll get you the documents. Okay, we're good? All right. And we're almost done with 6-1, except for, what about scenarios like this? Think top minus bottom. Isn't something weird happening? Like I just made this express, this is not going to pass the function test. By the way, this is the equation like x equals y squared. And, you know, it's kind of bizarre with the top minus bottom. You're like, the top is the bottom. You follow me? And so we're like, all right, we're going to have to look at those type of scenarios in a second. Oh, you know what to do. Oh, great, I'm coming to you. All right, so let me give you a picture. He's onto something. So we're talking about like, what do you do in situations like this, like x equals y squared, and as you're noticing, you're like, well, that's the top, that's the bottom, and gosh, I'm going to get the same kind of thing going on. It could get me confusing. So let me pick a problem. Hold up. Okay, when I made up one. Oh, this is number 12 from the textbook. So this is number 12 from section 6.1. I thought it was a good one. This is what they wrote. 4x plus y squared equals 12. And y equals x. And we've got to find the area between these two. Go find the area that's between those two curves. Although y equals x is just a straight line, isn't it? Okay. I'll get this out of the way. And we might write another formula over here on the board. Because this works fine when these are two what? Functions of x that pass the vertical line test and stuff. So let's make a decent drawing of this one. That's easy. That's just a straight line, everyone, right? You know what these graphs look like? This 4x plus y squared equals 12. If you solve for x, let's just see what we get. We get 12 what? Minus y squared. What will x equal? What's 12 divided 4? 3 minus y squared all over 4, right? Well, these things open up like this when it's x equals y squared, but isn't that x equal to a negative y squared? So how do you think this thing will open up? It's going to look like this. So I just want to point out, x equals y squared, just so it doesn't confuse you, if you haven't sketched these before. It opens up something like this, x equals a y squared. This is x equal to 3 minus a y squared. So this will look like this, correct? When I put the drawing here. Now, I'm going to sketch this. Let's make a pretty decent drawing here. These pictures are important. Make a picture. Can you help me find this x-intercept? I know this thing's just going to open up like this curve, because it's an x equal to a negative y squared. You might go up here. How do you find x-intercepts? What do you set equal to 0? Yeah, for an x-intercept, all we do is we set y equal to 0. I think you'll find it easier here. Would you set y equal to 0 and solve for x? What do you get? Is that negative 3? You know, for an x-intercept, so x equals what? There's 3 minus y squared. Cool. So in this case, I went 4x plus y squared equals 12. We're saying this is negative x squared plus 3. And in this case, if y equals 0, is x equal to just 3? I just want to make sure. Is that what I agree? Is that a point on that curve? 3 comma 0? Let me put it. It's the vertex, isn't it? But which way is this thing opening up? Like that. All right, let's do it. Doesn't have to be perfect. That's one of the curves. That's that curve, right? Shifted over 3, and then it what? Cool. But I wanted to do this. What I did was I just found the x-intercept. I thought it was the easy point to find to get this thing going. And then y equals 0. It hits this value of x equal to 3. That's not that bad, right? And it opens up like this. Hey, if it was an x equal to a y squared, it would look like this, wouldn't it? Cool. Now, we all know what that is. That's just a what? Straight line. All right, just make a straight line. Not drawing a scale, but look at this image carefully. That top minus bottom thing's not going to work here, Simber. I mean, you could still do it. It'd be much harder, though. So what we're going to do is prepare another equation up here. And you're onto it. So I'm going to go to you in a second. And when we look at this, look carefully at this image. From here to here, the top is the y equals x, and the bottom is the curve, right? What happens after that? Right up to that point right there. Who's the top? The curve, and who's the bottom? The curve. Do you follow me? Things switched in the middle wouldn't give us the correct answer. So, you had a great solution to this. He says, don't think top minus bottom. Think, what was it again? Say it again.
Right minus left.
Right minus left. He's saying when you get a scenario like this, where it's like, oh, the top was here, then it stopped being the top at this point, then this was the top. He says, think right minus left. So right now, can you do one of two things? Either think of this as right minus left and twist your head like me, but I don't want you to get a neck cramp. Or take your piece of paper and do what? Twist that. And do you see what he means? He says he's creating the same formula, except you're looking at it this way. I'm turning my head because I can't turn this green board, but you might just turn the paper to see that. So your equation was put everything in terms of y, but do right minus what? Left. Hey, that'll work. But the only thing is, we got to make sure we write all these variables in terms of what letter? Y. Brilliant. And when you notice the entire top, over here, from here to here, this is the right. From here to here is the left. It's always right over left. You see that? This is always the right side over the left side if you look at it that way. Cool. Now, which one of these is the right? I know you know. Which one's on the right side? You can write, and if you want to put a subscript of r for right, you can. X of r for the right side curve is the, what is it? 3 minus y squared over 4. Now, who's the left side curve? X equal to what? Here's x sub l. Here's the left side, right? X sub l is just equal to what letter? And I'll set up our problem. Right minus left. Who's on the right? 3 minus y squared over 4. And who's on the left? Y. Now we're going to look carefully. What letters do I have up here? They're all in terms of y, so I'm not putting a dx, I'm putting a dy. And we'll do this for scenarios like this. Yeah, you could have done top minus bottom, but that would have been a pain, right? We had to break it up into two expressions. Now, I'm challenged. Thank you for coming up with that. Very good. I'm challenged now with this. How do you get these numbers again? How do we find where they meet?
Set them equal to each other.
Set them equal to each other. Somebody might say, well, another way of saying that is substitute, right? So how about let's take this, substitute into this, and let's find, you got to be y values, right? You got to sense, there's one of the y values, right there. The other y value is way down here. Well, we got to find it. What are these two y values? So everyone, let's just go off to the side here. And we're going to say, I had 4x plus y squared equals 12. I'm going to get out of the way. I'm going to substitute for the letter x. What letter? Y. This is called the substitution method. All I'm doing, people say set one equal to each other. What I'm doing is setting that letter y in place of what the x was. It's the substitution method. Now when I got to factor that, so I'm going to subtract the 12 on this side. Y squared plus 4y minus 12 equals 0. Does anybody know two numbers to factor this? Multiply to negative 12, add up to 4. That was good. Positive 6 and negative 2. So what are the two y values for my limits of integration? Negative 6 is one of the y's, and the other y? You got it. 2, and this will give us the area. Ta-da! Will be a positive answer too. So far so good? Yeah? And we'll solve this. We'll solve this, everyone, but this will give us the area between those two extremes. So hey, I think you're discovering something. I guess the picture is really important, right? Yeah, we really want to get a sense of what they have there in terms of these drawings. What's the integral of 3? 3 what? What's the integral of minus y squared over 4? Y squared over 12, and y squared over 2. So I'm just going to write this out. 3 times what? 2 minus 2 cubed over 12 minus 4 2 squared over 2 minus, now I got to plug into what? The negative 6. What's 3 times? You got to be very careful with these negatives, don't you? Minus negative 6 cubed over 12 minus negative 6 squared over 2. So be careful with doing that arithmetic in there. Some of you may use the math 9 function off your calculators. Do you know what I'm talking about? Check this, very good. Known as a definite integral function on your TI-83s and 84s. You want to check that definite integral. But if you're going to put that on your calculator, just be careful. All this, subtract this quantity, we know the answer is going to come out positive. I did it earlier, everyone, if you want to crunch out all the math. Would you, just to check, you should get 64 thirds for your answer. Or 21.3 with a line over it, right? But right there, when you get to this step, you're just either doing the math mentally, on paper, using the technology to support you in finding these values. Just be careful with all those negatives, that's all I ask. And another thing, I saw the head nods like this. I asked students, hey, if you wanted to check to see what this answer is, you can use the math 9 function off those TI-83s and 84s that does definite integral calculations. If you're curious, like, can you show me how to do that? Oh, it'd take less than a minute for me to show you. Just wait till the end of class, what you gotta check. Sound good? And again, if I had this, backwards, I would have got negative 64 over 3. You can just put the bars in, right? Hey, cool. How many copies? Oh, we can all done copy. We don't have to solve the next one, but can we at least set it up? I think there's only one other scenario we got to talk about. I think you know what to do. So it's either top minus bottom or right minus left, right? Always works. It's amazing how this concept of right minus left can be very helpful in Calc 3 too. I do want you to think about that. It's a really important concept where you're going. Depends on the picture. How I'm going to look at this problem. I can erase. Are you sure? Yeah. You sure? I'm looking around. I want to erase before someone else. Yeah. Okay. Good. Nice. Hey, one more thing from 6-1. I mean, I'm talking about, let's just look at 2 simple trig expressions. Yes, sir.
On a test, do we have to show the antiderivative, like of us working all the way out, or can we just use the calculator?
So if you did this right here, after that step, you wouldn't have to show me any other math. You can use any method you want to come up with that final answer. Did that make sense?
Yeah.
So like you said it, but you would have to show the antiderivative. Okay. Good question. Show the antiderivative. Show your limits that you're plugging in there. Show that, hey, I'm going to plug these in like this.
Okay.
But then to get this, you might be like, well, I'm going to use the technology to facilitate the arithmetic.
Okay.
And I understand that, because that calculator has that tool. Great question. Great question. Yeah, at least show that antiderivative. Thank you. I'm going to have one more scenario. What if here you got something like these 2 curves? We're very familiar with these 2, right? I'm not going to go very far with them, too. Let's just go out to pi over 2. What does the sine curve do? Let me do this. And then they get up to what, a 1? What's the cosine curve do? And then it does this, right? So and what if I said, find the area between those bounded regions there, between sine and cosine, find the area between these 2, on this region right here, from 0 all the way to what? Look at the image carefully. And let me know. I'm going to write something on the board and I'm going to go to you first, okay? Because you came up with the last one. I'm looking at this. I see sine and cosine. We've been told this is the formula. So I want to know, will this work? Can I just go like this? Look, 0 to the power of 2. The top sine. The bottom cosine. Will that work? Something's wrong, isn't it? Do you notice? From here to here, who's the top? That's right. The top is the cosine. Starting here, who's the top? Sine. So how can we approach this problem? What do you think?
Split it in half.
All right, so you're saying, you want an integral, we're going to find this number here, right? Right now, you just want to call it A? We don't know it yet, just call it A. Do an integral from 0 to A. Who's the top? Cosine of x. Minus the sine of x dx. Then add that solution to, what's this? A to the power of 2. Who is the top? The sine of x. And who is the bottom? What we're saying is, we know how to approach this problem. You don't have to finish all this work here, right? And then we'll talk about that A guy. The key was the 7. But I know right now you're like, what the heck's that A? The key is we just knew how to approach this problem. Even Sean's awesome theorem from before wouldn't work here because of how they switched over in the middle. Right? So we had to handle it carefully and find out who was the top, who was the bottom, when did they stop, and then who became the top and who became the bottom, right? But do you all agree, we evaluate this, we're going to get the right answer? Cool. Now, does anybody know a common angle or sine of this angle is the same as the cosine of angle? It's between 0 and pi over 4. Does anybody know what that angle is?
Pi over 4.
This is 90 degrees. I heard it. What was it? 45 degrees, pi over 4. So if you're curious, what is that angle? I didn't want to make it too hard on you. You know, like, you sit there, should I use a calculator on that? It's that pi over 4. The cosine of pi over 4 is 1 over square root of 2. What's the sine of pi over 4? 1 over square root of 2. It's that 45 degrees. So I'm going to put that right here. That's where they met. And so we'll just put these A values, we didn't know this before, and we'll put that in there. There you go. And you don't have to work this out. I know you could. I know you could, but you don't have to. You know, keep going. I know you can do that. What's the integral of cosine? What's the integral of sine, right? So you don't have to finish this all out. Oh, by the way, this, good idea by the author. He put this as an example. So he put this on page 425. If you're curious, you want to look at this out of the textbook. There's an image of this, finding this area between them. Hey, I apologize. I should shade too. I didn't have this shade. Let me shade it. That was top minus bottom. And that's top minus bottom. This was cosine of x. This was sine of x. And then the top became the what? Sine of x. And who became the bottom? Cosine of x. They both intersected at 0 equal to pi over 2. But page 425, if you want to look at, all the writing on that, you can do this. And if it helps everyone with doing integrals of sines and cosines, go that way, you get integrals, right? So what's the integral of a cosine? Sine. What's the integral of a negative sine? Students write this on the papers all the time during the test. Just to help them determine the what? The antiderivatives. So it's just something I'll probably write from time to time, because sometimes you just don't want to mix up, is the integral of cosine sine, or is it negative sine? Is the integral of sine cosine, or is it negative cosine, right? You just want to be careful with that. So I'll write this from time to time. Cool. And these are just negatives. Alright? You know how to set this up, brilliant. That's every scenario. We saw the what? When it flips over at one point, sometimes it's good to do right minus left, depending on the image, or top minus bottom, ever you know how to find errors between curves. Cool. Right. You got it. You got it. Can I erase? Hey, in the notes, put 6.2. 6.2. This starts The other just writes volumes. I can erase these formulas. Okay, so erase this, put a 2 here, and we're just going to spend the rest of the class on volumes. We're going to take some region and think about revolving that solid around a certain x-axis or y-axis, one of the axes. So we'll start with this. How about just y equals x? We always start with a simple example. And when y equals x, just this time, let's go out from 0 to 2. You see that area right there? From 0 to 2. We're going to find the volume of the solid. That's an area. We're going to find the volume of the solid. All right? Such that this area is revolved around the x-axis to form that solid. So if this area right here gets revolved around the x-axis, like this, we're going to find the volume of that solid. Well, there's the area, y equals x. Take the area underneath y equals x, and this x-axis from 0 to 2, and let's find the volume of a solid. With a solid created, it's created by such that the area underneath this expression right here gets revolved around which axis? The x-axis. They have to specify which axis they're talking about, right? So, can we, in our notes, I know it's going three-dimensional now, right? Could we make a rough sketch of what that would look like, even though it's on a two-dimensional plane? If this thing's getting revolved around, and this would get revolved around, make a loop, and this would get revolved around, and this would get revolved around, and what would this end up looking like? A cone. Did you hear that? Someone said cone. Wouldn't this look like a cone? But like here. Just keep revolving this entire region all the way around the x-axis. It's making a three-dimensional solid, but it turns into a what? A cone. Well, the why is how do we approach this? It's very, very similar to doing area. Except that what we're going to do is we're going to take the summation. Alright? Integrals find summation, right? That elongated S for summation. We're going to sum a bunch of areas of disks. So this is the disk method. See all these disks in here? Think of it as a Riemann sum. But what am I going to sum up? An infinite amount of area of disks. The only thing is, someone's got to help me out. What's the formula for the area of a disk? I'm talking about a circle. Pi r squared. Oh, and here's our formula. We're just going to, you want to put the pi out here? Put the pi out in front of that integral, and let's just call this what? Radius squared, and we can call it function squared. Will that work? That's if it gets revolved around which axis, though. We should put that in the notes. I've got a pi, I've got an integral, f of x. We can put the a and b. You know what the a and b values are. What is it? 0 to what? I went out to 2, right? 0 to 2. The function squared, because isn't the function the radius? Isn't that the radius of this? Look. Isn't that the radius of this expression? Cool. But I'll put this in notes. If this gets revolved around which axis? REV for revolve. You could say about or around, about the x-axis. This method. Cool. Now, what if you got something like this? You know, when I'm talking about the region right here. 0 to 2, 0 to 2. This is still y equals x. Isn't y equal to x the same as x equals y? But what if I wanted this revolved around the y-axis? We need a formula for that. We need a formula for that. So you find the volume of the solid generated by revolving this area about the y-axis, right? And what would the image look like? Whoop, 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 whoop. It'd be three-dimensional, right? Wouldn't it look like this? So what's the formula? I bet you know. First of all, it's not going to be dx, it'll be what? dy. Function in terms of y. Pi radius squared, that's our radius. Pi r squared, that's our radius. And you get the two values for y, the limits of y. Pretty cool? All right, question.
How would you get the limits for the y?
Great question. Now, in this problem it was given to you. I know it was presented to you, 0 to 2. 0 to 2. So both of these, you would just go 0 to 2 and you'd find your answers. But I know what you're on to. You're like, well, what if you got to do it between two expressions? And that's where I'm going with. We're going to have to make a new formula, everyone. This was called the washer method. Washer method would be pretty easy. I mean, the disk method. I'm talking about, let's now look at the washer method. All right, so I'm going to put right here, put a line. What about a washer method? What's this for? Well, I'll go back to here. Remember this image before? Right there? What's a washer look like? Something like this, right? Now, if you were in a geometry class, and you had to get the area of this washer here, do you all agree I could just get the area of the bigger circle, and then subtract out the area of the what? The smaller circle. Wouldn't I get the area of this region? That's the formula we're looking at for the washer method. Okay? So what I'm going to present to you now is see y equals x. I'm going to stick it on the curve in here. How about, I did x squared before, I'm going to use x cubed. Get this out of the way. You know what x cubed does like a snake? I'm going to get this out of the way. Just erase this. And let's just take a curve. It goes like this. X cubed comes up like this. Then it comes around like this. Eventually it's going to meet that straight line. We're going to find, this is in 6.2. Let's find the volume of the solid that's generated by revolving the region between y equals x. What was my other curve? Y equals x cubed. I do want to point out, didn't I only put this in the first quadrant? So I'm going to make a note of that as well. Everyone, in quadrant 1 only. Because I think a lot of you would agree, we're going to find the volume of the solid generated by revolving the region in that first quadrant about the x-axis. So this thing's now going to get revolved around here. And we can make a pretty decent image, but I'm going to come back to you to find out what the heck we're going to use for those places where they meet. It's still that same method, isn't it? The intersection method. So when you want to make a rough sketch of what's going on here, this is y equal to x. This curve right here is what? Y equals x cubed. First, can we figure out where they met? I only took where they met in the first quadrant. Where did they meet? Somebody just do it in your head. What is x equal x cubed? Nothing tricky. X equal to 1. Does everyone agree? I mean, you could have done 1. X equals x cubed and solve that. But does everyone agree? Can you see it? These two functions here are meeting at 0 and at 1. So we already know the limits of integration. We're going to go from 0 to 1. The only thing is we need a math formula. It's something similar to what we were doing with area before. Like the area between curves, everyone? How can I get the volume of the solid generated by revolving this region about the x-axis? What the heck would it look like? If you want to make an image of this on your paper, everyone, it looks like what? This would come like this. This is what? Come be like this. If it reflected, and then this would just what? Whoop, 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 whoop. Something like this, right? And what would it look like? I can point you to some YouTube sites that looks way better. Okay, I'll direct you that. I can put those in Canvas as well. Where you can really see the what? The cool looking solid, you can look inside of it. Wouldn't it have like a little hole in there? Does everyone see that? Sounds like there's a gap in there. But we're going to get the volume of this solid. Then we need a formula. But it's something about a washer. What should I do? Pi r squared minus the other pi r squared. True? Will that work?
Yeah.
Remember we were talking about before, you said to find the area of a washer, you just take the area of the outer circle minus the area of the inner circle. So that'll be our math formula. Before it was just pi function squared. We can still just factor the pi out here, right? Because they'll both have pi's. And it'll be the, here, let's just call this the outer f of x squared minus the inner f of x squared. You want to use a different letter and put g? And let's call this one g. There's our math formula. Go from some what? A to some b. Outer and inner. Well, we'll talk about that. Who's the outer, who's the inner? So when I want you to look at this image, see, sometimes you might be going around the y-axis, okay? When I'm talking about the outer, I'm talking about the function that's furthest away from the axis of revolution. I should say that a few times. If you're wondering, what do I mean by outer? Look at your image. Which one of these two was further away from the axis of revolution? That's the one that's going there. The one that's further away, because that would be the outer what? Part of that washer. And you just, all you're doing is summing a bunch of washers. So which one is further away? I heard it. Here's the setup. We're going from 0 to 1, right? Isn't that where they met? 0 to 1. The outer is the x. Who's the inner? The x cubed. Now, what did I forget? This happens on test. Look carefully. You hearing us?
Pi.
This can happen. I just, you get partial, we're talking about partial credit. Look carefully, it happens. We just did area. There were no pi's in those area problems. Here you're doing the volume, and it's pi r squared minus pi r squared. Slap that pi down, right? Hey, Sean, are you ready? So, what if I had these mixed up? What's the saving method? Take care of it. She said, put absolute value bars where? You follow me? Again, we'll call it Sean's theorem, but she's saying, if you accidentally had the what? The outer and the inner mixed up, we're saying to save it, put your absolute value bars where? And you'll get the right answer. You really, with all that math? Yeah. You would discover because you get a negative answer. Hey, can we solve this? What's the integral of x squared? X cubed over 3. Is that x to the 5th or x to the 6th? Help me out. X to the 6th. That's where you multiply, right? What's the integral of x to the 6th? 7 over 7. 0 to 1, put your pi. One thing you got to help me out is, what is 1/3 minus